So, okay, is there like 1, 2, 3 cut, like in movies, or? Okay, I can start whenever I want. All right. Good morning, everyone. Thanks for coming. So the first, today we are going to talk about overview of the topics we are going to cover in this course, the historical perspective on blockchain, and the placement of the technology in the bigger picture and the bigger world of technologies. Before we start, I would like to immediately say that I welcome questions in the middle. So I like questions. I don't like too much to speak to myself all the time. So this is the program of the course. I mean, you already have access to the information. I just wanted to give an overview of different topics. So today, I already mentioned what we are going to cover. The first 3 lectures would be mostly about preliminaries. So the second, the third lecture would be about cryptographic preliminaries, hash functions, elliptic curve cryptography, zero-knowledge proofs. Then there would be a lab practice on also cryptographic preliminaries. So the students would be able to get some practical knowledge about the cryptographic technology. Topic number 4 would be an overview of the blockchain technology, its evolution, types, features, benefits, challenges, the architecture of blockchain and what it means for different systems and applications. Then we'll finally take a deeper technical dive into Bitcoin. So lectures 5 and 6 would be all about Bitcoin and its features. We give it the credit because it was the first technology, the first cryptocurrency that created the hype. Then we have tutorial still about cryptographic primitives, in this case zero knowledge. Topic number 7 would be mostly, again, the background history of consensus research and over the last 40 years. So it will be mostly history, but I will also briefly talk about the newest discoveries in this topic. So why are we given this background on cryptographic preliminaries and on consensus mechanism? Because blockchain is mostly a smart combination of different technologies. In order to understand blockchain, we need to know distributed systems, operating systems, storage systems, and security and cryptography. So the background is important. Lecture number 8 would be about creating more scalable solutions. So while blockchain provides a lot of benefits, it also has a challenge of scalability. It's known not to scale beyond certain limits. So, and people have been looking into ways to overcome that challenge. So lecture number 8 would be about different techniques to this end. Lecture number 9, and further on, we'll talk about different technologies related to blockchain other than Bitcoin. So after Bitcoin, there started a number of, there was significant interest in the technology, and a number of alternative solutions came, and we are going to take a deep dive into some of those solutions. So in lecture number 9, it would be Bitcoin NG and Algorand. So Bitcoin NG came from Cornell, while Algorand came from MIT. And today, most of the technologies actually originated from academia and later became practical currencies. Algorand is one of the top 10 currencies today. Then the next lecture would be about 2 additional blockchain systems, Stellar and Monero. Stellar came from Stanford. Monero is different in the sense that it's not came from academia. Monero has strong impact on privacy. It providing better privacy than Bitcoin. And in the next lecture, lecture number 11, we'll talk about even stronger privacy guarantees, systems with even stronger privacy guarantees, such as Zcash and the related technologies of Zcash snarks. And we'll talk about alternative mining. Then we'll have 2 lectures on Ethereum, where we'll talk about transactions, mining, and smart contracts. We'll also have 2 tutorials on Ethereum. So where you would learn how to work with the Ethereum tools. Then there would be a lecture about Hyperledger, which is not really a system. Hyperledger is an umbrella of different projects. Some of them complementing each other, some of them competing, some of them unrelated. So we'll take a look at the umbrella, and especially the flagship project within the umbrella called Fabric. What's uniting all those projects is that they're mostly oriented towards consortium blockchain as opposed to open blockchain. And in lecture number 4, we'll discuss the differences. Next lecture would be about Corda, which is yet another project within the Hyperledger umbrella, and about the Ripple system. And there would be a lab practice on Hyperledger blockchain as well. So most of the blockchain projects build a chain of blocks, or blockchain means a chain of blocks. So you can imagine a train where the blocks are connected. We'll be talking a lot about that structure. However, there are some more advanced systems which, instead of a linear chain, build a directed acyclic graph of blocks or transactions. And we are going to have 2 lectures dedicated to that topic. Then there will be a lecture about the blockchain security, different attacks on blockchain, and different defense mechanisms. And there would be a another Ethereum-related tutorial. Next, Dr. Chirag Moody will talk about smart contracts and vulnerabilities and solutions in the context of smart contracts. And there would be 2 lectures dedicated to digital identity management, which is a very important topic today. So there is a trend that of self-sovereign identity. And self-sovereign identity means that the subject of the identity should be able to have control over where the identity-related information is stored and with whom it's shared. So not the, say, the government or the entity or the university which issues the diploma, but say the student who gets the diploma will decide where the diploma is stored and with whom it's shared. Of course, there are very interesting questions related to security and privacy of such a scheme. So we are going to have 2 lectures about that. Then there will be a tutorial I previously mentioned where I would demonstrate different blockchain-related tools we developed, a simulator, and also generator of synthetic workload. In the next topic, there would be, well, the rest of the course would be mostly about different use cases. There would be 1 topic on a use case for real estate and supply chain management. There would be two lectures about blockchain for smart grid. And there would be a tutorial with case studies on certificate chain, property chain, and yet another lecture would be on e-governance and the remote voting. 1 lecture on the use of blockchain in healthcare, and yet another use case where blockchain is used for taxes and the legal documents. There would be a topic related to NFTs and metaverse. Another lecture would be on central bank digital currency, where there is a push to replace paper money in different countries with electronic funds, but still issued by the central bank. So the interaction with the central bank and individual vendors and also clients would be the main topic in that lecture. And finally, there is a lecture on blockchain-related storage, research-based development, and outlook for the future. So that is pretty much the structure of the course and the topics. If you have any questions, please feel free to ask. Okay. So before we get to it, I understand it may be a bit boring for the audience when the movie starts with credits rolling, but it's important to give credit when the credit is due. So most of the materials in this course is basically developed based on the courses I was given in different places. But originally, those courses started from a tutorial we as a team gave at the DEPS conference in 2018. And the tutorial is called Deconstructing Blockchain Concept Systems and Insights. And I'm grateful to all the authors of the tutorial whose material I'm reusing in this course. And I'm also very grateful to Dr. Chirag Moody for additional supporting material, as well as many discussions and helpful suggestions about how to improve the material of the course. All right, then without further ado, let's give an overview of the technology. So, blockchain. There are so many people using the keyword of blockchain, and also journalists. There are not so many people who understand what the technology actually is and how it's working. So hopefully, at the end of the course, you'll also be able to give a nice technical explanation about what the technology actually is. But let's take a look at how it all started. Because many people think that it all started in 2008, 2009, when Bitcoin came to existence. That couldn't be further away from the truth. The early research, so again, blockchain is a combination of several technologies, and all those technologies have been researched for maybe 40 years. So we can take a look at early research in cryptocurrency and consensus. It started from around 1983, before you had web browsers and before the internet became accessible to the masses. So the first system, or the first cryptocurrency system, is not Bitcoin. The first cryptocurrency system was DigiCash. It came out in 1989, like 20 years before Bitcoin. And as a matter of fact, again, before the internet became widely accessible to the masses, it was actually a relatively large scale, relatively popular cryptocurrency system for that time. What hinders its acceptance, or what hindered its acceptance, was that there were enough users who wanted to use the system, but there were not enough vendors who wanted to sell goods for cryptocurrency. And the system differentiated between vendors and buyers. So, in hindsight, there was an understanding this differentiation was prohibitive for the development of the technology. And later cryptocurrencies, such as Bitcoin, took the lesson to heart. So Bitcoin doesn't differentiate between different types of users for that reason. In general, Bitcoin is a smart combination of all the development up to this point. But okay, so in 2008, we had a Bitcoin white paper by Satoshi Nakamoto, whoever he is. And in January next year, there was open source release and deployment. So do you think it was a popular system at first? Someone can tell me what was the cost of a Bitcoin, one Bitcoin at that time? Sorry? Yeah, so you needed, yeah, exactly. It was in that order of magnitude. So you needed like maybe 100 Bitcoins to buy pizza, right? So what happened later? When did it become suddenly popular? So the first sign was when there was a financial crisis in Greece and Cyprus. And what happened is that the bank froze all financial assets. So the people couldn't take money, couldn't take the money and transfer it out of the country, which all the people wanted to do because they were scared of the crisis. And at this point, people realized that cryptocurrency is the way to do it. It was possible to buy cryptocurrencies in Cyprus, and then you can do it cryptocurrency in whatever you want. So this was the first realization that the cryptocurrencies can be actually popular. And this is also when the first academic interest started, right? The first appearance in wide news. So what happened next? The next important development was around 2013. By 2013, so what happened in the period between 2011 and 2013? Bitcoin became widely popular. However, it was not enough. What do I mean it was not enough? It was doing something very specific, but people wanted more functionality. How could we add more functionality? We couldn't do it directly in Bitcoin, so we had to take the source of Bitcoin, port it, do something else, and deploy a new system. And someone else wanted even more or different functionality, yet another new system. So by 2013, we had hundreds of systems spawn off from Bitcoin. And it became a jungle. Basically, people started to lose track of all those systems. And then there came a solution. So Ethereum was the platform that allowed for extensible development. So Vitalik Buterin, the inventor of Ethereum, was talking about the Swiss knife analogy. You know, Swiss knife is a knife with with many sharp ends of different shapes. So it's a single tool which could be used for 100 different things. And that was the idea behind Ethereum. And also at this point, people realized that the same principle so what united those different applications is creation of decentralized trust in an environment where the inherent trust is not present. So around 2013, people realized that there is a paradigm here. And the word blockchain came out. So before 2013, it was just Bitcoin. From 2013, people understood that it's more than just one system. And they started to use the term of blockchain. Yeah, so we had a long history of bubbles and bursts for Bitcoin and for other technologies. We had rapid development of and the emergence of new technologies. And so, for example, in 2017, the word blockchain overcomes Bitcoin in Google searches for the first time. So it was interesting that in India, sort of the interest of blockchain started a bit later. I was told that significant interest came around in 2019. But today, actually, India is one of the leading countries in terms of the use cases. Right. So that might be the reason why sort of the delay in the interest. But on the other hand, when people realize that it's not just about cryptocurrencies, this is where it all started. So what happens today? Blockchain penetration. Many governments in North America, Europe, Asia, coming up with their own blockchain-related strategy and legislation. So I'll talk about EBSI, which is Pan-European Blockchain Services Infrastructure. About more than 40% of top global banks have rolled out some commercial blockchain products. Microsoft at some point declared blockchain as a must-win technology for the business. IBM opened a new department, and there were dedicated labs and education programs in blockchain engineering popping out around the globe. So just some of the universities where those labs and education program originated. And of course, it also became a hot topic at many conferences, whether academic, whether societal, or whether industrial. A couple of words about EBSI. So what is EBSI? So in 2018, 29 countries of Europe, including, say, well, I'll not talk about the politics of Europe, but 29 countries have joined forces to create a joint European blockchain partnership, where the idea is to build a European blockchain service infrastructure. And the vision is to leverage blockchain for the creation of cross-border services, so that, for example, a diploma or, say, a vaccination certificate against COVID, against any disease, could be issued in one country, could be put on blockchain, and could be verified in the different countries. Because in Europe, there is a lot of cross-country, cross-border travel. So the idea is to use EBSI for public administration, for businesses, and also for individual citizens. I'm going to talk about EBSI in one of the lectures, so this was just a very brief overview. Now, what about blockchain? So if I had to present blockchain in one slide or blockchain 101, this would be it's also sometimes called distributed ledger technology, even though the two terms are not exactly the same. So blockchain is primarily a data structure. The data structure consists usually of a chain of blocks cryptographically linked to each other. So I'm going to talk in lecture number 4 about what it means to be cryptographically linked. Each block contains a number of transactions. Could be financial, but not necessarily. Could be any transactions in the broad sense of the word. And the data structure is replicated. So blockchain is formed, blockchain network is formed by individual nodes, sometimes called peers, and every node replicates the data structure. What you can see here in the illustration is the network between the peers. And the structure is very secure. What does it mean? You cannot alter any data which is already stored. You cannot delete any data which is already stored. The only operation which is allowed is to add new data in new block appended at the end of the structure. That's the only allowed operation. So, and even that operation is not taken easily. In order to append the block at the end, all nodes in the network need to run the consensus. It's like voting and agree, let's append the block. If they cannot agree, the block would not be accepted. And this is why consensus plays such a central role in the technology. And cryptography and security techniques are used in many places. It's used to encrypt the data, to prevent unwanted modifications, to gain a right to propose new blocks, to execute and verify transactions, and to create the ledger. These are just some examples. So blockchain is frequently compared with distributed databases. And sometimes there is confusion because people are just saying, okay, we could use distributed database or we could use blockchain. Blockchain is a replacement. Actually, that's not precise. There are some use cases where distributed databases are more suitable and other use cases where blockchain is more suitable. So there are two fundamental differences between distributed databases and blockchain, the way I see it. The first difference is that database is an organized collection of data representing the current system state. And the main functionality of the database is to allow efficient data retrieval, fusion, aggregation triggered by user queries. So it's all about viewing the data. In contrast, blockchain represents a ledger which is a history of transaction, or more generally, changes to the system state. So in blockchain, there is not even necessarily a concept of the state. You can calculate the state if you track the whole history of changes, which can be very long. But viewing and querying the state is not the main point of blockchain. So in Bitcoin, there is no such a thing as user balance. In Ethereum, there is user balance. It keeps track of the contract state, but it only provides very limited means to retrieve it, unlike databases. The point of the blockchain is not to query the state and process the data. It's not data processing. It's more data verification. So everything can be verified from the beginning until the end. Blockchain doesn't support query languages, data view, schema, join, and other database concepts. So as a result, another related difference is that Ethereum and other blockchain systems keep the entire history, and the history grows and grows. Nothing can be deleted. So it can become very large, right? It means that usually the storage space in blockchain is much more expensive than the storage space in databases. And so you need to be very careful. When you design a blockchain application, you need to think twice what you want to put on blockchain and what you do not want to put on blockchain. You don't want to put data on blockchain just in case. So that's another difference from databases. which are organized to store large volumes of data. So one common technique is to store some data off-chain, but to keep some indexes and some links and some security-related information to verify the correctness of the off-chain data. That you can store on-chain because it's much shorter, much more compact. And there is another major difference between blockchain and distributed databases. And that's the trust model. Distributed databases are usually set by the same organization. So even if the database is distributed, meaning it runs on multiple nodes, those nodes would be overall trusting each other. They would not be expecting attacks from within. And then, so collectively, all those nodes would be providing services related to the database. And of course, the users, the clients, may try to have access rights. So the clients may try to gain access to hack the database, to gain unauthorized accesses. So protection against attack from the clients is a major concern for distributed databases, but not necessarily attacks from within. Now let's compare that to blockchain. In blockchain distributed ledger, the trust boundaries are different. Say in Hyperledger, there is consortium, and each node would belong to one of the organizations. There are multiple organizations in the consortium. Those organizations do not necessarily trust each other. So they need to build the trust. They need to verify information to a much larger extent compared to distributed databases. On the other hand, the clients may sometimes come from the same organizations. So the clients may be even more trusted compared to distributed databases, depending on the setup. But overall, so there are variations here, but overall, the trust model can be quite different. So I see it as the two major differences between distributed databases and blockchain. So let's talk a little more about the terminology, Bitcoin and blockchain. So Bitcoin is a specific system. It's very concrete and specific thing. We know all about its design. There are so many documents. And if something is not documented, there is a reference implementation. So we can look up in the source and get the exact answer about anything we want. There is only one deployment of Bitcoin. And even though, as mentioned, like many systems originated from Bitcoin, and many other cryptocurrencies, many spin-offs with maybe just many forks, with just minor differences, but they are not called Bitcoin, so there is no confusion. Blockchain, on the other hand, is totally ambiguous. So it can be the data structure, chain of blocks. It can be the exact data structure of Bitcoin. It could be a separate concept. It could be a guiding design paradigm or principle. There are developing standards, but so far there is no strong standardization in blockchain. So people would say it's a generalization of Bitcoin, but in what direction, right? So in practice, like you ask people what is a blockchain, the number of different answers you will be getting will be approximately equal to the number of people you ask. So it's so varied and diverse. There are hundreds of different systems and implementations, and if you take Ethereum alone, so Ethereum, right? There is one major public deployment of Ethereum. But you can also take Ethereum and install it yourself on your computer, with your friends, within your organization. There are also hundreds of proprietary deployments of Ethereum. which you can configure to do something a bit different. So all this creates significant, well, sometimes confusion, but also the need to be very precise about when you talk about blockchain, what kind of blockchain you're talking about. Distributed ledger is a bit more commonly understood. So as mentioned, it's an append-only log storing transactions comprised of immutable blocks of data. It cannot be tampered with. It must be deterministically verifiable, and it's able to execute transaction programmatically. It's fully replicated, and it's decentralized. So it does not rely on a third party for trust. And still, if you look at the literature, you would be finding many different definitions of blockchain. This is an example. So as an example, I'll give you 5 different definitions, and they're all used. Definition 1. It's a system that uses the blockchain structure, exact blockchain structure of Bitcoin, but extend the functionality. So it could extend the business logic. It could slightly tweak, adapt the consensus protocol. Definition number 2, it's a system that maintains a chain of block. Could be a structure other than of Bitcoin, for example, in Ethereum. Definition 3, it's a system that maintains a ledger with all transactions, but not necessarily stored as a chain of blocks. This is the case in IOTA and other cryptocurrency using directed acyclic graph. Definition number 4, it's a system with distributed non-trusting parties collaborating without a trusting intermediary. That's the definition adopted in the Corda system. And definition 5 is probably the most frivolous. It's a system that uses smart contracts. So the last 2 definitions are more about actually how blockchain is used and what it is. Well, the good news is that the people do agree about the main benefits of using the technology. And the main benefits is that it enables parties who do not fully trust each other to form and maintain consensus about existence, status, and evolution of a set of shared paths. And this is its main benefit, so the main feature, the main principle which benefits in blockchain-based infrastructures. And the second main benefit is the ecosystem of smart contracts, about which we are going to talk a lot in this course. So I'm going to repeat these benefits many times in the duration of the course. So far, this is just a very high level overview. Now we are going to start with the origins with the background on, in this case, on consensus. And in the next lecture, I'll be given a background on cryptographic primitives. So the research in consensus started in about 1982, when basically the following problem was considered. Imagine that you have several armies surrounding the city, and they want to attack the city. If they coordinate their attack, they manage to sack the city. If, however, they do not coordinate well, and only one of the armies attacks the city, the army will be defeated. So coordination, very important. So there is one distinguished process, the commander, which proposes initial value. And the value could be attack or retreat. A retreat meaning let's not attack at this time, let's attack at a different time. And the other processes, and the commanders of the armies, say the lieutenants, communicate the commander value between each other and make sure that they all agree on the outcome, so it would never happen that just one army attacks. What's the problem? The problem actually, like, it has significant historical interest. In the Byzantine Empire, the generals were known for his treachery. So sometimes they would prefer to see the other general destroyed than to attack the city. So they were really malicious, and they could betray the other armies. So they could lie. For example, a lieutenant can say to the other lieutenant, I heard that the commander told us to attack. Well, in fact, there was no such command. What happens? If the other lieutenant would mindlessly attack the city, it would be the only army attacking the city, and the army would be destroyed. So the assumption is that there are Byzantine processes, Byzantine coming from the Byzantine Empire, and there are correct processes for like the good lieutenants who are telling the truth. And even commander can be Byzantine. So what do we want to achieve? Consensus means that if the commander is correct, then all correct processes should agree on the proposed value. And if the commander is faulty, then all correct processes would agree on a value, but not necessarily the value which was sent by the commander. So let's take a look at a few scenarios. This is a scenario with four nodes, of which one can be Byzantine. And the Byzantine node is colored in a different color. Okay, so in this, what happens in this scenario? The node, okay, so the commander would send a certain value V to all of the lieutenants. Okay. Now, this lieutenant is Byzantine. So it would tell, okay, about the notation. 1 means that this is the first round of communication. V means this is the value sent. Okay? So in this case, the commander is honest, sent 1V to everyone, and say Lieutenant P2 process 2 sent message to 1V, 2 meaning round number 2, and the message saying, in the first round, I saw the value of V from the commander. Okay, so this is, P2 is honest. However, P3 is Byzantine. So it will be sending 3.1U to P2 and 3.1W to P4, where U and W are just random spurious values. So in this case, would they reach a consensus? Would the honest nodes reach a consensus? Well, the answer is yes, because each node could look at the majority of the messages it's getting, and the majority would all say V. So the fact that there is one U here would not, okay, so majority of V, VU is still V. So P2 can, based on majority, decide that the value should be V. Now P4 would do the same. So P2 and P4, the honest lieutenants, would reach the same conclusion. And the consensus is achieved. This is the second case, is the case of a Byzantine commander. And here, the commander was sending two different values. Now, what happens here is that there is no majority. So each process would see that no value is getting a majority. U was only sent by one process, V was only sent by one process, and W was only sent by one process, no majority. So P2 decides on a special value, like a faulty value. And again, all the processes, all the honest lieutenants reach the same conclusion. So that's still a good scenario. Now, this is a case with 3 nodes. So there are 2 different scenarios. In the first scenario, P3 is Byzantine, and the second scenario, the commander is Byzantine. And in the first scenario, let's look at both scenarios and see what P2 is doing. So P2 in the first scenario is getting the value of V from the honest commander, and it's getting the value of U from P3, which is Byzantine. Okay, so there is no majority. The second scenario, the commander is Byzantine. The commander sent different value, V and U, to different lieutenants. However, P2 is not able to distinguish between the 2 scenarios. In both cases, it's getting V from the commander and U from the other lieutenant. So it doesn't know what to do, which value is the correct one. And thus, consensus is not achievable. So this underlies a major impossibility result. There is a major theoretical impossibility result that if at least 1/3 of the processes of the nodes are Byzantine, consensus cannot be reached. So we can see it in a very simple scenario with 3 nodes, but that result, that impossibility result, can be generalized if at least 1/3 or more of the nodes are Byzantine, no consensus can be reached. The result can be alleviated, mitigated with digital signatures. So if every message is signed, the result doesn't exactly hold. Okay, that's the same scenario, but with digital signatures. So in this scenario, P3 cannot forge P1 signature. So when reporting to P2 about what it heard from the commander, it would not be able to forge, to change the value, because the value of 1V was signed. And when forwarding the message to P2, it would also need to forward the signature from the commander. And it's not able to forge the signature and tamper with the message. And in the second scenario, it would be if P1 is the faulty commander, it would send 2 different messages. Both messages would be signed. And if P3 forwards the message from the commander with the signature to P2, then P2 will see that commander actually sent 2 signed messages with different values. And that means that the commander is faulty. So the detection can be achieved with digital signatures. The problem, however, is that in practice, it has been shown that digital signatures cannot always be relied upon. And this is why the strongest Byzantine resilience means that we cannot rely on digital signatures. So this is the end of the first lecture. Thank you, and please ask questions. Okay. Initially, it was a purely theoretical exercise, inspired, however, by the historic evidence. But the problem of consensus was like in the early 80s, it was purely theoretical. Yeah, in the lecture on consensus, I'll talk more about it. But yeah, later they tried to verify the result on maybe like 4 different nodes. So in the 90s, like a large scale consensus system would run on 4 servers, right? But this is where it started, and then sort of there was a question of how to scale. In the lecture on consensus, I'll tell you a bit about what Google is doing with consensus-related services today. So it depends. It depends which model, right? So Byzantine fault tolerance is just one of several strands of consensus, right? So there are different types of consensus. Like this is not the type used in Bitcoin, but this is used in Hyperledger Fabric, for example. This type of consensus. So it's known. Actually, it's able to achieve pretty fast transaction throughput. Transaction throughput can be very high in like a order of thousands of transactions per second. So much higher than in Bitcoin. The problem of scalability here is actually with the number of nodes, not with the rate of transactions and not with the number of times they're trying to agree. The worst case that could happen is that there is one node which is occasionally acting as normal, and occasionally Byzantine, and occasionally it's delaying messages. And then, one of the biggest issues in consensus, in this type of consensus algorithm, is inability to distinguish between a process which became slow for a brief period of time and a process which is inherently faulty. And the process can appear slow okay. So imagine there is Alice, Bob, and Carol. And Carol acts slow, and Carol doesn't like Bob, so it acts slow in communication with Bob, but she's very fast in communication with Alice. So now Alice and Bob trying to understand what to do with Carol, or whether Carol should be whether Carol is Byzantine, whether Carol is faulty. So Alice say, hey, I have no problem with Carol. Bob say, I have a problem with Carol. So now Alice and Bob would be a discussion, right? And because of this, just to give an indication, because of this, in modern consensus implementation, like the fault detection sometimes may take minutes to be on the secure side. Minutes. So this is the Achilles heel, the weakness of this type of consensus algorithm. But on the other hand, it can achieve much faster throughput. So could you speak up, please? Proof of work? Not related. There are many different types of consensus algorithm. This is not proof of work. I'm going to talk about proof of work in lecture number 5 or 4. Yeah. Sorry, about implementation of what? Yeah, of course. The lecture on consensus is going to give. So yeah. I mean, I'm not able to present all of the course content all at once in the first lecture. Sorry. But if after hearing the lecture on consensus you still have the question, please ask. So the second lecture in the course would be, and the third lecture would be about cryptographic preliminaries. So why do we need so much cryptography before we can even start talking about blockchain? Well, because it's used in blockchain for many different purposes. It's used to encrypt data. It's used to prevent unwanted modifications. So the immutability or resilience to tampering of the blockchain structure is due to use of cryptography. When you propose new blocks, there are many consensus algorithms, and some of them are heavily relying on cryptography, such as proof of work. So in proof of work, in order to gain the right to propose a block, you need to solve the crypto puzzle, and that requires, so what is a crypto puzzle? In order to understand that, and in order to understand why it works, you need to have a background in cryptography. When executing transactions need to be verified, and general data need to be verified, and the verification is due to signatures and cryptographic data structures. So cryptography again. And sometimes in order to verify the inclusion of a transaction in a block, you use data structures, cryptographic data structures such as Merkle tree, which are also based on cryptography. So that's why. I'm not going to, this is not a course in cryptography, I'm just briefly covering the relevant cryptographic primitives and parts. So in blockchain, we are mostly using asymmetric cryptography with the public key and the private key. The idea was conceptualized by Diffie and Hellman in 1976. So in asymmetric cryptography, there is a pair of keys, one public, one private. And for example, Alice can sign messages with her private key, while everyone else can verify that indeed it was Alice who wrote the message by using the public key of Alice. Public key verifies. The other use is that everyone can encrypt the message to Alice with her public key, but then only Alice will be able to decrypt it and read the message, no one else. So the use of public cryptography in blockchain is so typical because the blockchain is not based on one-to-one interaction, where say symmetric cryptography might be more applicable. In blockchain, you have, for example, one sender of the message, and then the entire world would be welcome to check the ledger and verify the transaction. So hence the need for asymmetric cryptography. Okay, so asymmetric cryptography, we need a key pair. How do we generate a key pair? What are the requirements? Well, the construction of the pair needs to be fast. It should be fast when we use the key, when we encrypt, or when we sign messages, and when we verify. That the usage of the keys must be fast. And that means that the keys need to be short. So of course, the shorter the key, the faster it is, but it's less secure with the shorter key. It's easier to guess the key if the key is short. So there is a trade-off in terms of the key length. And of course, the other requirement is that guessing the private key based on the public key needs to be hard. How do we achieve this hardness? How do we construct the keys? So the hardness of guessing the public key is due to the existence of what's called one-way functions. And again, there is heavy math involved, but I'm just giving an overview. The gist of the one-way functions is that they're fast to compute, but it takes a lot of time to inverse the function. It's hard to inverse the function. So several ideas have been proposed, like regarding which one of a functions to use. The first idea was the RSA function proposed in 1977. Today, most of the ideas are based on the problem which is called generalized discrete log problem. What's the problem? We are given a finite cyclic multiplicative group. Okay, I'll immediately give a realistic example. So we could create a group of natural numbers or remainders of division by certain primary integer. So, for example, 7 or 11. How would we form such a group? The group would consist of all the natural numbers from 1 to 6. If the primary number used to generate the group is 11, then it would be all natural numbers from 1 to 10. Okay, so what's the operation? The operation is multiplication. The group is multiplicative. So, for example, if you want to take a multiplication of 5 and 7, group up to 7, so let's take 3 and 4. 3 times 4 is 12, but we compute the remainder of 7, so it would be 5. The multiplication of 3 and 4 is 5 in this group. That's the operation. Now, why is it cyclic? Cyclic means that there is a generator number. In the case of the group of 7, it would be 3. So we can, 3, what is the generator number? It means that we take the generator number and put it different degrees, square, to the third, to the fourth, and so on. And this way, we are able to generate all members of the group. So for this group of created by the prime number of 7, the generator would be 3, and 3 to the second 9, 2, 3 to the third 6, 3 to the fourth 4, 3 to the fifth 5, 3 to the sixth 1, and 3 to the 7 is 3 again. So we exhausted all the members of that group. And this is why the group is cyclic. And actually there is a theorem saying that if the number is primary, then any group created this way would be cyclic and would have a generator. Okay, so that was an exemplification of the cyclic multiplicative group. But what's the problem of the discrete log? The problem is the following. We take any two members of the group, and the problem is to find the logarithm of one element based on the second element. For example, given 1 and 3, we need to find the degree to which we need raise 3 in order to get 1. Okay? So in this group, it happens to be equal to 6, as we see, because 3 to the 6 is equal to 1. But the problem is to how to find that at 6. That's the problem. So which one? Yeah. 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 3 to the 3 is okay. 3 to the 3 is 27, right? 27 divided by 7 is 6. The remainder is like it's 21. 27 minus 21 is 6. The remainder is 6. They are computing remainders. Okay. Okay, so that's the idea. Now let's see the application. So how do we do it? How do we construct the keys? So how do we build a cryptographic public key cryptography based on this problem of generalized discrete log? Okay, so the group and one member of the group are selected a priori and known to everyone in the world. So, for example, we know that it's a group of numbers of 1 to 6. Well, this is, of course, a very small group. The practical group would be much, much bigger. But anyway, the group is known a priori, and we pick one member of the group, such as 3, a priori, beforehand. And we make sure everyone knows what they are. Now, suppose Alice wants to generate her own key pair, the public key and the private key. What does she do? Alice picks a random number k, which becomes her private key. Then Alice takes, calculates b to the degree of k. Okay, how would and a becomes her public key. Now, how can Alice calculate a efficiently? How can Alice calculate b to the degree of k efficiently? Well, the naive algorithm would be to take b and just multiply it k times. But that would require k multiplications, and k can be very big in practice. So that's a lot of operations. We don't want that. What would be a faster way to calculate b to the degree of k? Yeah, I mean, it's just it's a simple. It's like well, it's not exactly a binary division, but what you do is that you divide k by half, and you calculate sort of square root of b to the k, and then if you know how to calculate the square root of b to the k, then we can calculate the square just in one operation, and then we take k by half. Okay, how do we calculate to the degree of k by half? We calculate b to the degree of k by 4. And again, calculate the square. And this way, instead of doing k multiplications, they are doing logarithm of k multiplications, which is much faster. So this is why generating the public key is efficient for Alice. Okay, now, how difficult would be for an attacker? So what is the attacker given? The attacker is given A, and of course everyone knows G and P. How difficult, how hard would it be for the attacker to restore K? To hack the system and figure out what the private key K is? Let's see. So the brute force algorithm is so we have B, we have A, and we have G. What can we do? Well, we can just take B and start multiplying it by itself. To the second, to the third, just a brute force. That would take a number of operations which is linear with K. Because the attacker doesn't know K, the attacker cannot do this trick which Alice did. The attacker cannot divide K by half and get number of operations which is logarithmic with K. The attacker needs to do it in a linear way. And that's much more inefficient. So in practice, against the brute force attack, a key length of, say, binary key of length 80 bit is considered again already secure because 2 to the 80 is operations is already a large number that, say, for a common user, for a common hacker, it's already difficult to break. Okay, but is brute force the best the attacker can do? Can the attacker do better than brute force? So the best known algorithm for calculating K, if we know A, B, and G, so best known algorithm that work for an arbitrary case would take an order of the square root of the size of G. So not linear with G, but a square root. Still, square root is much, much bigger than logarithm of K. So it's still much harder for the attacker to figure K than for Alice to calculate the public key. So square root means that in order to be secure in practice, you need a key maybe of length 160 bit instead of 80 bit. So twice the number because of the square root. So that's the general idea. Now, okay, so so the general discrete log problem. There are still questions remaining. In practice, what group should we take? I mean, I was showing you the case of division by 7, right? The group which is generated by the primary number of 7. In practice, of course, this is way too small. This is just to illustrate the concept. Okay, so what would be practical? What would be a good group to use in practice? So there are different proposals. Early proposals, and perhaps still the most popular case today, is to use such groups based on primary numbers. But of course, instead of 7, we'll be maybe taking like numbers order of 2 to the 80, right? But we still need a prime number. Okay, so that's probably the most well-known case, and it has been heavily explored. We know all the results related to the security of using private public keys based on such groups. What's the problem? The problem is that the number theory gives attacker much better tools than the general algorithm. So the best known general algorithm takes order of square root of the size of G for the attacker. But that's the general algorithm. For specific groups, the attacker can do much better. And it turns out that for this group of numbers, the attacker can do much better. There are specialized algorithms, specialized attacks for this group. So, for example, I previously said in general case the 160-bit would already be secure. Well, for this group, a key of length 795 is known to have been broken in 2019. So 795 bits is much bigger than 160 bits, and yet it has been broken. In reality, systems using such keys, using this system of this kind of group, would be using keys of over 2,000 bits. And 2,000 bits is quite a lot. Maybe not a lot to send over the network, but it's a lot to, like, again, we need to generate keys, we need to apply keys for the signatures. And the longer the keys, the more time we take on that. So, and of course, if we include some stuff on the blockchain, the storage space on the blockchain is expensive, as we said. So you want to be as short as possible. So that's why this is not considered the best group. And this is why blockchain is not used in this group. What does blockchain use? It's using elliptic curves. Before explaining what it is, I'll just explain why it's much better. So elliptic curves allow for significant reduction in key size. An elliptic curve cryptographic key of 163 bits is equivalent to, in terms of security guarantees, to the RSA keys of 1024 bits. And if you do 256 bits with elliptic curve cryptography, it's equivalent to the RSA key of 3000 plus bits. So it's much shorter, and we are getting the same guarantees in terms of security. And this plot in the slide shows basically the benefits, or how hard it would be to break elliptic key cryptography compared to, say, RSA. Right? So here we see that that's the key size, and on the x-axis we have in terms of year of operations. So you can see that if you want to achieve significant security or increase the time to break the key significantly, then you can see that the curve for RSA is much worse than the curve for ECC. Okay, now let me again give a brief explanation about what elliptic curves are. Elliptic curves are not ellipses. It's even though it sounds very similar. So what are elliptic curves? It's a plain algebraic curve which consists of solutions like, okay, so it's two-dimensional space, right? What you see here is two-dimensional space. And two-dimensional space, and we have an equation with two variables, x and y. And it's an algebraic curve which consists of all solutions, x and y the coordinates, for the points on the solution, in which y squared is equal to x to the third plus a plus b, where a and b are coefficients. So a typical elliptic curve looks like this. Well, of course, depending on the values of a and b, they would look different. Okay, so that's an elliptic curve, but how we define operations? How do we define a group based on elliptic curves? The operation is the following one. In most cases, a line which would intersect an elliptic curve would intersect it in 3 points, like in this example. It's not always the case. I mean, well, obviously I can put a curve here, a line here, and then it would be no intersection at all, but or I can put it on a tangent as a tangent, right? And then it would be only 2 points instead of 3. But most lines would intercept in 3 points. Okay, so what's the operation? The operation is the following one. For example, P and Q. And then, draw the line. We find the third point, in this case minus r, and we invert it. We are finding this point at the end. Result of the operation. It's called like, if it would be denoted as a summation, it could be also called multiplication. I mean, using the plus sign, but we could use any other sign, right? Of P and Q. That's the main operation with the elliptic curve. Okay, so we also need to be, okay, there are examples. But before we come, we need to say that potential element of infinity, which is a bit counterintuitive. It's sitting over there like it's in addition to the curve itself. And that element is 0. So, for example, if it is R and R, so the curve would be like this. And in this case, there is no curve point. We imagine that there's like one point at infinity. And we call this point 0. So that's a special point. Okay. So some examples. P plus Q plus R would be equal to 0. Similar to this case. Because P plus Q would be equal to minus R, and R plus minus R is equal to 0. P plus Q, so here we have a tangent, right? So what do we do with the tangent? In this case, we say that P plus Q plus okay. The additional point, like the third point of the tangent, they say that it is it would be like Q itself and accordingly minus Q. So if you have a tangent, say that that the result of the operation would be minus Q. There are also similar cases, so we could go over different cases, but this is the gist. Like there are corner cases. I'm not covering all corner cases, but this is the gist of the operation on the elliptic curves. This is the geometric interpretation. There is also algebraic interpretation of all those operations, but it's more complicated, so I'm not covering it. However, any book on cryptography would also cover the algebraic interpretation of elliptic curves. So here is an example of an elliptic curve with the coefficients of 2 and 1. So for this, we can see that for this specific curve, all points would form a cyclic group with the generating point of 5 with the coordinates of 5 and 1. So I'm not showing exactly how it's computed, but you would need to trust me that 2p would be equal to 0.63, 3p would be equal to 0.106, and then if you go to 18p, then we'll get minus p, and 9p would be equal to 0. For this specific curve. So this is just an example. Okay, so this is the idea of working with elliptic curves. Now, how can we extend this to a cryptographic system? We are still working with a generalized log problem. However, instead of working with natural numbers, we are now working with elliptic curves to compute the multiplication in the logarithm. How to do it? Alex still picks a degree key, which is a secret key. And Alex takes some well-known elliptic curve. Again, elliptic curve would be known to everyone. It's like the group. And the generator of the group would also be known to everyone. So Alice takes the generator and calculates p to the degree of k, where k is the secret key. And again, it can be done. It can be done more efficiently. It can be done in time logarithmic with k, in the same way. So, and the attacker would need to calculate k. However, because we are not working with natural number any longer, we are working with elliptic curves, turns out that there are no well-known attacks on elliptic curves, such as we have on natural numbers. And therefore, breaking cryptography based on elliptic curves is harder. Okay, but of course, like, there are some catches and downsides. The first catch is that not every elliptic curve is good for cryptography. We cannot just take a random coefficients and say, okay, let's try this elliptic curve. That would not work. So there are standardization institutes that research, explore different elliptic curves, and decide which one are better suited for cryptography and which one are worse. So this, for example, the NIT in the US issues verified curves, which everyone is supposed to use. There are additional downsides of elliptic curves. Some of them are patented. Some may have trapdoors. Some of the elliptic curves were developed by NSA or in collaboration with NSA. And people are a bit afraid that NSA actually knows how to break the elliptic curves. So it could tap into the communication. Also, theoretical foundations for elliptic curves is not as well developed and as understood as, say, for RSA or for the group of generated by prime numbers. So certain properties are unproven, but they seem to hold in practice. People believe them to be true, but people are not 100% certain. Still, like, the certainty is enough that the system would be used in practice, and especially used in practice by resource-constrained devices, such as IoT devices, cell phones. You also need to be a bit careful when selecting the random numbers and the generators. So that's the background on elliptic key, overview of elliptic key cryptography. Again, this is the type of cryptography used in blockchain, what generated public and private keys. Speak up, please. Oh, random number generator. My bad. Well, they all look okay. I mean, most elliptic curves look like this, like there is slightly the stretch. Most elliptic shape, elliptic curves have this shape. And again, issues this is what they use in the blockchain. What would depend on application? Yeah, well, again, the idea is that the key generated this way is much shorter, right? So the key size, this is the reason to go for this. This is the reason why resource-constrained devices such as mobile phones would want, or even sensors, right, would want to go for this kind of cryptography and not for RSA. Okay, the other primitive we are going to cover in this lecture, other cryptographic primitive, is hash functions. So what's the idea of hash functions? well, the hash function have many uses, right? So what is a hash function? Hash function takes long data of arbitrary length and produces short data of fixed length. So you can think of the hash value, so it's called like the result of applying the hash function. The short data of fixed length has many names. It can be hash value, hash code, digest, sometimes even hash itself. So the terminology is varied, but usually it doesn't create any confusion. So we can think of the hash value of the digest as a fixed size fingerprint, short fixed size fingerprint over large variable size data. Okay. How do we use hashes? The digest may act as an identifier representing the data. So instead of comparing the data and seeing, okay, is it the same piece of data or is it a different piece of data? It would be much more efficient to compare the hash value because it's much shorter. So the digest is used in digital signatures, right? So what is a digital signature? We can take a document of arbitrary length, no matter how long it is, and produce a signature of a fixed size. And we use it for verification, right? But of course, there are many other uses of hash functions. CRC. So, for example, I download something from the internet. I want to verify that it's not fake, that it has not been tampered with, that I downloaded it correctly, right, without any data corruption. How do I do it? I calculate the hash, and I compare it with the announced hash of the data. And I see it's the same. Okay, if it's the same, that most likely I downloaded the right piece of information. The same for messages, right? So data integrity. This is the second use of hash functions. And of course, we also use it as a keys, say for hash tables. So this is how we can store the data. And there are also a few other uses of it. It's one of the most popular primitives in computer science. Okay. But what is a good hash function? What do we exactly want from a hash function? Well, we said it takes arbitrary length input and calculate fixed size output. Yeah? But what else? Well, we need to be able to do it efficiently as usual. So we cannot do too heavy of a computation. We want to minimize the collision. What does it mean? Usually we take large input and compact it, compress it. This is what the hash function does, into a short output. What does it mean? It means that the input space is much bigger than the output space. In that case, it means that multiple values of the input would be mapped by the hash function to the same output, or they may be mapped to the same output. That's necessarily the case because the output space is smaller than the input space. So if two different values of input map to the same output, that's called a collision. And it's not a good situation. Why? Because it breaks all the nice properties. We cannot use it. What's the use of the ID if it's unique, right? If my passport may turn out to look exactly as the passport of some other person, it's a problem. So therefore, it's important to minimize the collision or to minimize the probability of collision. So what does it mean in practice? In practice, if we assume that the input values are equally probable, there are no very popular input values and not so popular input values, then ideally in that case, we want the hash function to spread it uniformly over the output space. If however, the input distribution look different, then maybe we need a more specialized hash function. Now, when we use it for cryptography, as we do in blockchain, there are additional requirements related to security. The first requirement is a hash function should be one-way. one way means that it's based, like if I'm given the hash, it would be very difficult for me to restore the original input value. So based on the signature, I can verify the signature. It doesn't mean I am allowed to read the content of the original document. Second requirement is called weak collision resistance. So what is a weak collision resistance? If you are given a hash value, it's difficult to find an input that hashes to that hash value. It doesn't mean the input that was used to produce the hash value. It could be any other due to collisions, so there could be collisions, right? Small number of collisions. But for the attacker, it should be difficult to find an input value that produces the collision. If there are collisions, doesn't mean it's easy for the attacker to find the collision. So, so why is it an important requirement? Because otherwise, I could, for example, in a file sharing system or any system that uses, say, CRC for data redundancy, or that includes some verification code in the message when sending a message, right? If someone intercepts the message and finds a different message that maps to the same hash, then the attacker could easily replace the original message and break the signature. So that's not good. The third requirement related to security is called strong collision resistance. So the second requirement was weak collision resistance. The third requirement is called strong collision resistance. And the further strong collision resistance means that it's difficult to find two inputs that hash to the same value. Now, I'll also give an example of an attack that, so if you don't have strong collision resistance, I can show you how it can be exploited in an attack. But before I do that, I want to remark that strong collision resistance is a much more stringent requirement. It's much more difficult to satisfy compared to weak collision resistance. That's because of the birthday paradox. So, how many of you are familiar with the birthday paradox? Please raise your hands. I can see. Okay, then I'll explain to you what a birthday paradox is, because many of the students are not familiar with it. Birthday paradox. Okay, so let's say I'm born on the 10th of October, which is just an arbitrary value. But now I'm thinking, what's that, like, how many people are here? Okay, let's think it's 90? You said? Yeah. I think a bit fewer, maybe 80, like it looks like 80, but that's, I mean, anyway, that's the order of magnitude. Okay. So what's the probability that one of you is born on the same day as I am? What's the probability? Well, okay, so there are 365 days in a year, and there is, like, for one of you, the probability that you are born on the same day as I is 1 by 365, and the probability that the other person is born on a different day is 364 by 365, right? Okay, now, that's for one person. But let's say you are 80 here, or 90. Then, what's the probability that none of you is born on the same day as I am? That would be that number to the degree of 90. Which I actually, like, I calculated. I think it's about 0.6 0.78. So with the probability of 0.78, none of the same day as I am. Okay, now let's do the test. Who is born on the 10th of October? Is there a person here? Okay, no one, right? So 0.78 is sufficiently high probability. Okay. What does it mean? What's the application? This calculation is applicable to weak collision resistance. Because the attacker would need to go individually over different input spaces, right? And see if the hash value would be the same as the given hash value, right? This is what the attacker would need to do in order to break weak collision resistance. And the probability of each input value mapping to the same hash value is the same as what I did in this calculation, right? Well, depending on the space, right? In this case, the space was 365 years. It's 365 days. But of course, the realistic space is much bigger, right? So it's very difficult to break weak collision resistance. Now, I'll ask a different question. What's the probability that two people in this room are born on the same day? The calculation in this case would be totally different. So suppose, like, okay. So if you take one person, one other person, it would be like the probability of not being born on the 10th of October would be the same. But now we have two people with two different birthdays. So what's the probability of the third person to not have a collision? It would be 363 by 365. The probability for a fourth person would be 362 by 365. And so on. So it would not be like this number to the degree of 90. Each time, the probability for each next person, the probability of not having a collision is becoming smaller and smaller. And as a result, for 90 people, the probability of two of you having birthday on the same day would actually be, I believe, around 90%. So here, the probability to be successful was around 0.22, and 0.78 was the probability of the attack not being successful. For the two of you, for having a pair of people with the same birthday in this room, the probability of a successful attack would be more than 0.09, and the probability of withstanding resilience to the attack would be less than 0.1. So with high probability, two of you have birthday on the same day. Do you see how it relates to our discussion of hash functions? Can someone say? So it relates to strong collision resistance. Strong collision resistance means it's difficult to find two inputs that hash to the same value. So if there are two people, if there are two input values that hash to the same value, there's a problem, according to strong collision resistance. And the probabilities are calculated in the same way as in the birthday paradox. As a matter of fact, why is it called the birthday paradox? Because it's enough to have 23 people in the classroom so that the probability of having a pair with the same birthday would become more than a half. Only 23 people, which is a very small classroom. So this is why it's much more difficult to withstand attacks on strong collision than attacks on weak collision. All right, now, how do we exploit the strong collision? And so let's consider that Mr. Big Shot has a dishonest assistant called Mr. Creepy, and who would be preparing contracts from Mr. Big Shot's digital signature. Okay, how can Mr. Creepy launch an attack? So Mr. Creepy prepares the legal contract for a transaction. Mr. Creepy then proceeds to create a large number of variations of the legal contract without altering the important content. For example, Mr. Creepy can add a white space here or there, unnoticeable, but many variations. Then, Mr. Creepy would be given the contracts, all the collection of contracts to Mr. Big Shot for digital signature, and Mr. Big Shot would sign all those contracts. Now, Mr. Creepy has all those signed contracts in his possession. Now, Mr. Creepy also prepares a fraudulent version of the contract. And as with correct version, Mr. Creepy prepares a large number of fraudulent or variations of the fraudulent version of the contract. And the contract, say, the fraudulent contract would be, say, exploiting something or doing something illegal. So, so we have two sets of contracts. And the first one would be signed by Mr. Big Shot. The second one would not. But with a big probability, there would be a pair of contracts, one from good contracts and one fraudulent contract. There would be a pair such that the hash value, the digital signature, would be the same, like in the birthday paradox. Okay, now, so that's the idea of how to exploit or how to launch an attack on strong collision. How do we implement hash functions? I don't have a lot of time to speak about implementation of hash functions. Again, there are nice books on cryptography which can give you details, but again, I'm just giving a brief overview. A hash function is typically based on internal compression function that works on fixed size input blocks. So the initial message would be broken into blocks of certain size, and the number of such blocks is unlimited, or at least can be very large. There is no restriction on the total length of the input. And we take the first block and compress it calculate the hash value. Now, for the second block, we take the hash value from the first block and feed it into the compression function along with the second block. And the compression function would calculate the second hash value. And this way we'll continue with the next block and the next block. And the output would be the final hash value. So this is how the scheme works. So it looks like a chain block cipher, right? So produces a hash value for each fixed size block based on its content, and hash value for the previous block. And one of the properties is what's called the avalanche effect. If we just change one bit in the input, all most likely all bits of the hash value would look different. So one change in the input, dramatic effect on the output. So, so this is like the theory of hash functions. But what do we do? What do we use in practice? In practice, the most popular, again, the hash function, like finding good hash function is not easy. And there are standardized hash functions that everyone is using and that researchers have analyzed and verified the good properties. So you shouldn't just come up with a hash function on your own. You should take one of the standard ones. Okay, but what are the properties of the standard ones? The most popular functions are coming from the MD family. So it all started by the MD5 algorithm, which is not used any longer. It's not considered secure any longer, but it started the family of hash functions. Okay. What you see here in this table is the algorithm, the number of output bits, the number of input bits in the block. It's like this, the size of this block. That's the number of input bits. Again, the total input can be unlimited. And each hash function like calculates many rounds, right? So tries to scramble the bits, like takes one round of calculation on the input block, and then does another round and another round. So the number of rounds varies across different hash functions. So here you can see the summarization about the number of rounds. And perhaps the most important is the last one, how likely the collision is. So for MD5, people are not using because it's easy to break and collisions have been found. The next sort of family of hash functions, well, still without MD5, is called SHA. And SHA, SHA, stands for Secure Hash Algorithm. So the first proposed SHA algorithm within the family is called SHA-1. And it's still in use pretty much. It has been broken, but it's not easy to break it, right? So like a typical, but if you want to break one instance of SHA-1 hash function, then it's estimated that you need to spend an order of $50,000 on the infrastructure. So doable, but probably like a common person would not be doing that. Still, if you want to be more secure, you need to use more advanced SHA functions. So the recommended standardized SHA functions are SHA-224, 256, 384, 512. Collectively, they are called SHA-2. So the nomenclature, the naming is a bit confusing, right? So SHA-1, SHA-2. And in particular, Bitcoin is, and many other cryptocurrencies are using SHA-256. That's the one standardized in Bitcoin. As a matter of fact, there is already a new standard, SHA-3, but its adoption, it's newer, it's faster, it's even more secure. But it's not as widely adopted yet. Why? Because first of all, like SHA-2 is already fast enough and secure enough. So there is no significant push to change something that's working to something that's even better, right? And the infrastructure is there, and changing the infrastructure always takes time. So that's why SHA-3 is not as popular yet. But at some point, it may replace those. So this is pretty much the end of the lecture. I would like to thank you for your attention. And even though I was welcoming questions in the middle as well, I hope to get some now. Thank you. Which algorithm?
Yeah, you said to us that there is a certain type of algorithm in SETI. There was an algorithm that you mentioned.
I've mentioned several different algorithms. I don't know. I'm not sure which one.
Bloom something. Bloom or Bloom?
Bloom filter. Bloom filter. Bloom. Okay, I can write it down.
Yeah.
Okay. So we are ready to start with the third lecture, which is still cryptographic preliminaries, but it's a different topic within cryptography. And it's quite a fascinating topic for me. I mean, I'm not exactly doing this area, but the other day I was watching a movie how they explain it to kids in primary school, and I really like it. So it's called zero knowledge proofs. What is a zero knowledge proof? So here I would be using a lot of material from a tutorial on zero knowledge proofs called a server of zero knowledge proofs with the application to cryptography. So I think it's a very nice survey for those who would like to familiarize themselves with this topic. But let's start a bit with let's start with some preliminaries. We already mentioned one-way functions. Easy to compute on every input. What is easy to compute? It means there is a polynomial time algorithm to compute. Yet difficult to invert, meaning given the output, it's very difficult to find the input on which the function was applied to produce that output. So any polynomial time randomized algorithm succeeds with negligible probability to, given the output, to find the original input. Okay, what does it mean difficult? Here we need to be careful. Because in computer science, we associate difficulty with NP-hardness. This is not the case for, this is not what we use for one-way functions. Why? Because NP-hardness means that there are some difficult instances. So in a problem, we have a lot of different instances, right? On which the problem can be applied. You know, graph coloring, we can have a lot of different graphs. Traveling salesman, we can have a lot of different city combinations and Hamiltonian paths. So every classical NP-hard problem would have a lot of instances. But it doesn't mean that all instances are equally hard to solve. NP-hardness means that there is at least one hard instance which would be very difficult to solve. It doesn't mean that all instances would be difficult to solve. NP-hardness doesn't mean that an average, a typical instance would be difficult to solve. So NP-hardness only talks about the worst case. That's not enough for us. We want the average case to be hard, not just the worst case. Because in cryptography, it's not enough that sometimes digital signatures would be difficult to break. We want digital signatures to be hard to break all the time, not just sometimes. So it's different from NP-hardness. So we also will be using in the notation of collision-free hash function about which I was talking previously. So some examples of one-way functions which are used in cryptography and in particular in zero-proof systems. First example, multiplication of two large numbers So given two large numbers, it's easy to calculate their product. And by easy, I mean it's polynomial with the number of bits representing each of these two numbers. However, if we take the product and we try to find the two numbers, ooh, that's a hard problem. Hard in the sense that there is no polynomial algorithm, polynomial with the number of bits in the product, which would give us the factorization, the two factors together, whose product is together creating the given number. Like I take even, okay, one of my favorite prime numbers, 239. So 239, if I give you, if I give you 239 and say I ask you to compute 239 square, you would be able to do it easily. If I give you that value and ask you, give me the factors, try to figure out that okay, I'm not saying it's a square of some, I'm saying it's a product of two numbers. Give me those numbers. You would not be able to find those numbers easily. So that's a one-way function. Easy to compute one direction, difficult to compute the other direction. Another example is squaring modulo number. So we take a number which is a product of two prime numbers. So n. So we take some p and q prime numbers, compute their product, would be n, and now we build, we consider the, I think it would be the ring of numbers calculated by x square modulo n. So we take an input x, and we calculate the square, and we calculate the remainder modulo n. And that's the output. Now, if I give you x, you would be able to calculate the function very easily, very efficiently. If I give you the remainder and ask you, give me the x that produced the remainder, that's a hard problem. Okay, so that's just one-way functions. It's not the fun part yet. Now, so what is a zero-knowledge proof? First of all, what's the proof system? Suppose the prover wants to convince the verifier that a given statement is true. So the age, for example, okay, well, the example. I want to buy alcohol in a store. I need to provide the proof of age, right? So I want to convince the verifier that my age is within the certain range. I want to provide the proof that a person is vaccinated against certain disease, right? That's a proof. I want to say, I want to convince you that I possess some secret key. That's a proof. So a proof is called complete if an honest verifier will always be convinced of a true statement by an honest prover. A proof is sound if a cheating prover, so suppose I'm underage, but I'm saying my age is 21, okay? So I'm a cheating prover. Then I can only convince an honest verifier that some false statement is true with a small probability. I am not requesting that the probability be 0. I'm okay with a small probability of cheating. Now, a proof system is interactive if the prover is allowed multiple rounds of communication with the verifier. So the verifier can be, okay, it's like security check. Okay, like first question, you answer, okay. Now the second question, okay. Now the third question. That's interactive proof. Now, what is zero knowledge? So that was the proof system. Now, the zero knowledge part. Zero knowledge means that not only I want to prove the statement, I want the verifier to learn nothing but the veracity of that statement. For example, I want to prove that my age is above 21. I don't want you to know what my age is. I just want to convince you that it's above 21. I don't want to disclose my age. I want to convince you that I possess a secret key. I don't want to show you the key. I don't want you to learn nothing except for the fact that I possess the key. So, formally speaking, a proof is called zero knowledge if the output of any strategy used by a curious verifier could also be produced by non-interactive calculation. So in other words, whatever information can be learned by interacting, by like, I'm a verifier, I'll be asking prover a lot of questions. All I can learn can also be extracted from the initial information without any interaction. In other words, I learn nothing apart from the statement itself and its veracity. I mean, usually the first reaction, is it even possible? How can I convince you that I have a secret without showing you that I have it? It's quite surprising result. Yes, I can, due to one-way functions. And what we are going to spend most time on in this lecture is I'm going to give you examples of different zero knowledge proof systems. So I'll be sort of trying to show that they indeed are proof systems, complete, sound, and they're also zero knowledge. And later I'll also explain, so zero knowledge is heavily used in blockchain. It's also used in many applications such as digital identities and verifiable credentials. All right, let's start. The first example is like is a simple example. A magical cave. So the cave has a magic door deep inside that opens only when you say a secret word. And it happens that the prover, Peggy, discovered or uncovered the secret word. Now, the verifier called Victor hears about this fact and wishes also to know the secret. So Peggy agrees to sell Victor the secret word for $1,000, for $1 million. However, before Victor is willing to pay that much money, Victor wants to make sure that Peggy does know the word, that Peggy is not cheating. Okay, how can Victor learn or make sure, get convinced that Peggy knows the word without learning the word? So here's the system to do it. Okay, by the way, just to make sure that's the shape of the system, right? So the magic word in the middle, it then opens only when when you know the word. So here's the idea for Peggy. Victor will wait outside the cave while Peggy enters. Now, Peggy can choose path A or B at random. All right, so Victor doesn't know which path she has chosen. Then, okay, so you can see it in the illustration here. All right? So Peggy chooses one path at random, goes to the door, and waits. Then Victor enters the cave and goes to the fork, and at the fork shouts, tells the Peggy which way he wants Peggy to return. He shouts, way A or way B. And Peggy would hear Victor, right? And if Victor shouts the same path for which Peggy entered, Peggy would come back the same way. If Victor shouts the other path, Peggy would say the secret word, the door would open, and Peggy would come out. So, completeness. Peggy will always be able to return along the required path, right? If she knows the secret. If Peggy is honest. Soundness. Let's suppose Peggy doesn't know the secret. What's the probability with which Peggy would be able to comply with Victor's request? Sorry? Yeah, 1/2. Yeah, 50. Exactly. Okay, you could say, well, 50 is still a big number, right? So it's like, it's too generous for a cheater. Okay, what we can do, we can repeat the tests multiple times. And Victor would only accept the statement as true if Peggy passes the test each time. Just once Peggy fails, Victor would reject. And this way, so 2 times, the probability would not be 50, it would be 25%. Then when 1/8, so 1/4, then 1/8, 1/16, so it's exponential, right? And we can get it as small as we want. We are not demanding that it will be 0, but we can get it as small as we want. Zero knowledge. Victor doesn't learn the secret word. Okay, so that was a simple example. Now let's take a look at more complicated examples of zero knowledge proofs, which I also use in practice. Example 2. A proof for graph isomorphism. What is a graph isomorphism? 2 graphs with the same set of nodes are called isomorphic if and only if there is a mapping between the nodes of the 2 graphs. So essentially, it's a mapping to itself, or a permutation, such that the edge in the first graph would correspond to the edge in the second graph after the permutation. Here's an example of the 2 graphs, right? So here we have a rectangle. Here we have this shape of a butterfly or something. Is it isomorphic? Can we have a mapping? It's the same nodes, right? Can we map the nodes of this graph to nodes of this graph so that the edges would correspond? The answer is yes. Maybe, I mean, it's nice sometimes when the students can explain why it's the case, please. Why there is an isomorphism? In this case, what's the mapping? All right, well, the mapping is written here. So this node maps to this node maps to this node. This node, however, maps to this node, and this node maps to this node, right? And then we have the same edges here as we have here. So the same connections between the nodes. So the two graphs are isomorphic. And okay, so what you see here, this mapping is a permutation, right? It's a mapping between the nodes, the set of nodes, to the same set of nodes. Permutation. Now we can say that that a graph is a random isomorphic copy of a different graph if it's obtained by picking a permutation, right? In just the notation. How can we use all this to create a zero knowledge proof system? So what's the idea? The thing about graph isomorphism is that if I know the permutation, I can easily verify it. So suppose we are given two graphs, and the two graphs are isomorphic. So let's denote the isomorphism between the two graphs. They are isomorphic, we know that. V as the prover, right? So, however, the thing is, if we don't know phi, it's very difficult to say in the general case if the two graphs are isomorphic. I mean, what we saw in the previous slide was just a very small scale, right? If we give like large scale two graphs and ask, are they isomorphic? And we don't give you the permutation, it's very easy to find out if there is such a permutation and what it is. That's the one-way function. So the idea of the proof is as following. We are executing 4 steps, certain number of times, and each time we are using independent random coin tosses. If the verifier completes all iterations successfully, then he accepts, otherwise one failure and the verifier rejects. So what happens at each step? The prover selects a random permutation and generates a new graph H, which is a random isomorphic copy of G1. So we have G0, G1. G1 isomorphic. Which are isomorphic. We take G1, we take a random permutation, and we produce a new graph H, which is isomorphic to G1. And the isomorphism is transitive, meaning it's also isomorphic to G0. Okay. Then the prover sends the graph to the verifier. The verifier chooses at random a coefficient, either 0 or 1, and sends it to the prover. Now, what happens is if the coefficient is equal to 1, then the prover sends the permutation to the verifier. Not the original permutation, not phi. Phi is the secret. It sends phi. This permutation to the verifier, not this permutation. If the coefficient, however, is 0, then the prover calculates pi times phi and sends that to the prover, to the verifier, sorry. Okay, so what happens is that the verifier gets all the data and calculates, checks if there is isomorphism between G alpha and H. I mean, how? If alpha is equal to 1, then the verifier does the same calculation that the prover earlier did. It just computes. So it gets pi from the prover. It takes G1, applies pi, gets H, and if it's the verifier already knows H, if it's the same H, then it works. The verifier accepts. If alpha is equal to 0, then the verifier takes G0, not G1, applies pi times phi, right? And pi times phi applied to G0 means that, well, phi applied to G0 is G1, and pi applied to G1 is again H. So the verifier would accept. This is the verification. Now properties, completeness. If a prover knows the original isomorphism, that is phi, then the prover will always be able to answer the test. Soundness, if a prover does not know phi, then again, the probability for one so if the prover doesn't know phi, it means that the prover will still be able to calculate a random isomorphic copy of G1. So if alpha is equal to 1, then the cheating prover would still be able to send correct answer to the verifier. However, if alpha is equal to 0, then the prover would not be able to satisfy the request of the verifier. So with probability 1/2, the verification fails. And again, we can repeat it m times. So at the end, the probability, the prover who is cheating, who doesn't know the answer, would be able to answer the request with probability 1 to 1 divided by 2 to the n. So zero knowledge. It's also interesting to see that the whole scheme does not disclose phi. It only discloses pi times phi, and it's not possible because the verifier doesn't get pi. It only gets pi times phi. So from pi times phi, it's not, because we don't know pi, it's not possible to restore pi. And therefore, it's zero knowledge. So it's also possible to prove that actually the verifier doesn't learn anything which is not in the proof. In practice, okay, those are just some examples, but in practice, most zero-knowledge proof schemes are based on the Fiat-Shamir protocol. Okay, how does the Fiat-Shamir protocol work? There is initialization, it's yet another proof, right? System. Initialization. We have some trusted center, like some trusted authority, which selects and publishes n equal to the product of two prime numbers. So the trusted center keeps the two prime numbers secret, but discloses their product. And we know that factoring numbers is a hard problem, so it's given n, it's difficult to find p and q. Now, the prover selects a secret s, secret value, which is co-prime to n. So s is a number between 1 and n minus 1 including. And then the prover computes square root of s modulo n, which is like we denote as v, and discloses v as the public key together with so like publishes t, uses t. You can think of t as maybe like a ledger, open ledger or blockchain, right? So the prover can put the public value of V in the blockchain open to everyone. Now again, we know that it's a one-way function, so given V, we cannot easily calculate S. S is a secret. V is public. Again, P and Q secret, S secret, N public, and V public. Okay? So the goal is for the prover to convince the verifier that, that the prover possesses the private key S without disclosing S. So how can the prover do that? As usual, it's based on interactions, right? So the steps are executed a certain number of times, each time using independent random coin tosses. And if the verifier has completed all steps, he accepts. So that's common for many proof systems, but what each step does is different. So each step consists of two phases. In the first phase, the prover chooses a random number and sends the square root modulo n of that random number to the verifier without disclosing r, only x, only the square root. The verifier randomly selects a bit 0, 1 and sends back to the prover, and then the phase 2 starts. In the second phase, the prover computes and sends to the verifier a value, which is either r if e is equal to 0, or it's equal to r times s modulo n if e is equal to 1. So then the verifier checks the following. If y is equal to 0, if y is equal to 0, or if y squared is not equal to x times v to the e modulo n, then the verifier rejects. Otherwise, the verifier accepts. And we go to the next iteration. So I mean, it's a bit involved, right? So let's take a look at a running example. Let's say that the center, the trusted center, picked P and Q, the two prime numbers, and calculated their product, which is 35. And the 35 is published to everyone, while 5 and 7 are kept secret. Now Peggy, the prover, secretly chooses 16. 16 is a coprime to 35 because they don't have any common denominator. She calculates 16 squared modulo 35, which is 11. And that's the public key of Peggy. Okay, let's take a look at how the protocol could run, say for 2 iterations. First iteration, Peggy randomly selects a value, say 10 in this example. She would calculate the value of 10 squared modulo 35, which is equal to 30, to Victor. And you can check that r squared 10 is indeed like modulo 35 is equal to 30. Okay. Victor randomly selects a bit, in this case 0, and sends back to Peggy. And since the bit is 0, Peggy just sends back r itself, which is 10. And Victor verifies that r squared is R square modular modulo 35 is equal to 30. Then the second iteration starts. This time, Peggy selects a different value, r equal to 20. She would calculate the square of 20, modulo 35, which is equal to 15, and sends it to Victor. And this time, Victor selects not 0, but 1. And since Victor selected 1, Peggy computes S16 times R20 modulo 35 equal to 5 and sends back to Victor. And Victor verifies, indeed, that y squared, so meaning 5 squared is 25, and times and modulo 35 is the same as 15 times 11. So this is how it works. I mean, it's a bit involved, but this is how actually most practical zero knowledge proof work. So they use this kind of math. So the properties. Completeness. A prover who knows the secret key will always be able to answer the request correctly. As usual, in one iteration, a prover who doesn't know the answer, who doesn't know the secret number, would only be able to satisfy the request from the prover if E is equal to 0. If E is equal to 1, Peggy would not be able to correctly compute the answer. So the probability of failing in one iteration is again half. And the zero knowledge, at no step, Peggy discloses S itself. So the secret is safe. These are some examples of the zero knowledge proofs. And in several lectures further down the course, you'll see the application. Again, this is preliminary, so you have not seen how we are going to use it, but that you are going to see in the rest of the course. So thanks a lot for listening.